Okay, so good morning, everyone, and thank you, Mr. Chairman. I will share my screen and start my presentation. Okay, so my name is Ricardo Batista, and I will present the work entitled High Resolution Crack Tip Displacement Field Applications using Numerical Methods. This is a joint work between IDMEC and Engenharia, and it's also developed by Virginia Infante, Madalena Garcia, Carlos Esteves, Daniel Braga, Bezat Farahani e Pedro Moreira. Okay, so in my presentation, I will briefly explain our motivation. I will also briefly touch upon fracture mechanics and the finite element analysis that we are using. And then I will show you our numerical and some experimental results, and of course, end with our conclusions for now. Okay, so what is our main motivation, our main goal for this work? Our main goal is the need to create a numerical model that accurately simulates the behavior of fatigue pre-cracked specimens under static loading. And on Monday, Bezat has already shown us some of these experimental results, and now we will show you our numerical modeling. So what are the goals of this numerical model? Of course, with numerical models, we can always perform some cost reduction when analyzing the behavior of fracture propagation on metallic materials. Also, the engineering challenge of solving the complexity of material fracture propagation at a microscopic level, and we can use these numerical models in order to better understand how propagation works. So we are talking about fracture mechanics, which is a branch of solid mechanics. It is applied to the selection of materials and design of parts and assemblies. And it can be used to define the maintenance process, complementing non-destructive techniques. It's also aimed at the maximization of the minimization, of the possibility of a crack failure on a part or on a component structure. And in this case, we are using the finite element analysis method to perform our numerical simulations. The finite element analysis technique is a numerical modeling technique of mechanical behaviors of parts and assemblies. It minimizes the design phase and also reduces the costs and duration time associated with this task. Allows for higher design flexibility, and of course requires prior validation with the experimental work. And this is exactly what we are showing here, is the validation of our numerical model, comparing it to the experimental results. Okay, so once again, we are creating the model for two empty specimens. These specimens are loaded in tension, and the results were recorded by both direct image correlation, or DIC, and electronic speckle pattern interferometry, or ISPI. The pre-cracks that we are analyzing with two different lanes were created by fatigue by cyclic loading with a maximum load of 10 kilonewtons, a load ratio of 0.1, and a loading frequency of about 12 Hertz. In order to simulate not just the final static loading of the cracks, of the crack specimens, we also wanted to simulate the whole fatigue process of the specimen, because during this fatigue test, as we know, there will be plastic strain accumulation along the crack front. And we wanted to capture this effect in order to compare it with the experimental results. So we created, for now, a 2D plane stress model with finite elements. It's also a symmetric model, so we are just simulating half of the specimen, because we are using the release node technique in order to simulate the fatigue process. So we are creating the model and applying a dynamic load. And in each load step, after one load application, one cycle application, we are releasing a node on the symmetry plane. This represents, therefore, in each increment, crack growth increment, and it corresponds to a given number of cycles that we are not focusing right now. But the release node technique allows us to analyze the fatigue process throughout the whole test and simulate the accumulation of plastic strains. The node was released at the maximum load. Some authors also consider the possibility of releasing the node on the minimum load on the cycle. And for now, we are just considering a simple material model, which is a plastic perfect model. Around the crack tip and on the area of the plastic deformation, the element size is for now around 100 nanometers. So here are some of the already shown experimental results. As we can see from both the ISPI or the DIC images, as the load increases, we can see a very large zone with some plastic deformation. And this plastic deformation is visible throughout the whole crack front, as we can see here. And this is exactly what we wanted to simulate with our numerical model. Using the strain and stress fields, we can also use these results to calculate the stress intensity factor using an overdeterministic calculation algorithm. And we have also applied the same algorithm to our numerical results in order to also calculate the stress intensity factor. So as we can see, this is for the MT2 specimen, a specimen with a small crack. And we can see that the numerical model is already capturing the plastic accumulation or plastic wake around the crack front. You can see here or here in this higher detail. And then we have the classical bean-shaped stress or strain field distribution around the crack front. So we are getting already some very good correspondence between the numerical or the experimental and the numerical results. The plastic zone for the MT2 specimen, the plastic zone size is about 747 nanometers, and we have also used this size and dimension to validate the model. Regarding the stress intensity factor, as we can see, and compare with the ISTM standard value, we are getting a good correspondence between the numerical, the experimental results, and of course, the standard value, which is about 345 megapascal square millimeters. So we are obtaining good correspondence and agreement between all the solutions. Regarding the specimen with a higher length crack, as we can see here for the MT4 specimen, the crack is longer, but we are still getting the plastic wake around the crack front. And also with our simulations, with our numerical model, we can predict the size and the full dimension of the plastic wake around the crack front. And then, of course, the same strain and stress distribution around the crack tip. Again, we can compare these final results for the higher load applied to the specimen in both the numerical and the experimental, and the numerical results. Finally, the plastic zone was also calculated. Of course, we have a bigger crack, so now the plastic zone is higher. And of course, we also checked if this was correct. Regarding the stress intensity factor, both the numerical and the experimental results now also have a higher error, but the difference is still not very high, and it may be also connected with the difference between the right and the left side of the crack and the values that are being used to calculate the stress intensity factors. So we have successfully matched both ISPI and DIC displacement and strains fields with the numerical model, which is a full fatigue simulation that allows for the residual plastic strain accumulation determination, or the determination of the plastic wake. We have also acceptable deviation between the stress intensity factors for both DIC and ISPI experimental results and our numerical simulation. This numerical simulation is now only using about 7 to 15 elements within the plastic zone, which is not a very high number. So the next steps will be, of course, to create a 3D model with a finer mesh, with more than 30 elements within the plastic zone. That should, of course, improve our results. So I hope you have enjoyed our presentation, and thank you for everyone.